And it's a great pleasure to have Mark Zhandry tell us about.
Yeah, so my wife's a minimalist, so I guess I caught on a little, and this talk is going to be so much about minimalism that there's no results, just some opinions. All right, so typically in classical crypto, there's this refrain that one-way functions are the minimal cryptographic assumption. We put in our theorem statements from the minimal assumption of one-way functions, blah blah blah, and this is just taken as fact now. So we can view things by looking at Crypto Mountain, where we have all the primitives you might care about. Up in space there, we have obfuscation and other ones in case you missed it. We typically treat one-way functions as being on the bottom of this mountain. However, a pretty cool sequence of works has shown that actually there's something below one-way functions once we enter quantum. And so there's this whole sea now of these less than one-way function computational assumptions that we could plausibly make in the quantum space. And the point of this talk is to just explore what should be the new minimal quantum crypto assumption. So actually, most of this talk is going to have nothing to do with quantum at all. And what I'm going to do for the bulk of it is review what I think of are the reasons that make one-way functions minimal for classical crypto. And once we have those reasons, maybe we can start to try to understand what to look for in the quantum setting. Okay, so the obvious thing to start from is just and I'll call this feature 0, is that one-way functions are implied by essentially everything in crypto. So in a feasibility sense, they are minimal because if you can do anything, you can do one-way functions, at least anything in the computational setting. But this is not satisfying because one of the famous results from symmetric key crypto is that one-way functions are actually really powerful in the sense that we can if we have one-way functions, we can do almost all of symmetric key crypto, and we can even do some public key crypto like signatures. So what is stopping us from calling signatures the minimal crypto assumption? Why don't we have all of our theorem statements say from the minimal assumption of signatures? Okay. So now I want to describe a handful of features that one-way functions have that all of these other things may or may not have, that I think really make one-way functions a nice thing to be kind of the central hub that we call a minimal assumption. So I'm going to first update feature 0 to feature 1. And I want that whatever object we're talking about, in order for it to be minimal, not only is it implied by almost everything, but it should actually be rather trivially implied by almost everything. So for example, going from one-way functions to signatures is extremely complex, relies on a number of really foundational and surprising results in classical cryptography. You have one-way functions of pseudorandom generators. From there, you go to PRFs. Then you have the signature trees and all that. It's really quite a complex construction. So it's highly non-trivial to go from one-way functions to signatures, but almost everything rather trivially implies one-way functions. This isn't quite true. Really, the really obvious way that you would try to get a one-way function from a lot of cryptographic primitives is really it only gives you a distributional one-way function, which says that it's a different requirement. It's not that it's hard to invert, but it's actually hard to sample from the distribution of preimages. So almost everything trivially gives you a distributional one-way function. It's pretty close to a one-way function though, and they do imply each other. So this one's a little bit hand wavy, I guess. But again, like the goal is to find something where you're not having to do this enormous complex thing to try to build your assumption from the rest of crypto. It should just be really direct and simple.
Not to the top, there's a question.
Yes.
Just to point out, that's not the correct reference. So it's Mike Luby, not Stephen Rudish.
Okay. Sorry about that. Yeah.
I suggest something more? One-way functions have very low Kolmogorov complexity.
Sure.
I mean, just three letters.
Even compared to distributional one-way functions, I feel one-way functions are much easier to tell somebody about.
Yeah, and I'll like kind of touch on that. I have 7 more features to go, and we'll. I won't call it any longer of complexity, but those are kind of touched on. Okay, so closely related is when we're actually going to not just instantiate from other general crypto assumptions, but when we actually want to instantiate from concrete assumptions. Again, we want it to be trivially implied by most concrete assumptions. And it's trivial that discrete log, factoring, learning with errors, isogenies, like almost any crypto assumption that you might want to use, trivially implies one-way functions. It actually implies one-way functions, not having to go through distributional one-way functions or anything like that. And in contrast, if you want to go from like discrete log to signatures, and you don't care, and you don't want random oracles, you have to work pretty hard. Another sort of sub feature of feature 2 is that I want the implication to be rather robust. And I think looking at discrete log versus DDH is a good example of this. So the fact that the discrete log is a one-way function that's rather trivial, but it's a one-way function even if you kind of play around with the function a little, right? If you sample x uniformly in the domain of exponents, it's still one way. If you sample x uniformly as n-bit strings, where n is log of p, it's still one way. If you choose x from a subgroup of the exponent space, as long as it's almost everything, it's still one way. What was that? I mean, the regular notion of one-way functions, strong one-way functions. And contrast this with DDH, where whether or not the assumption holds is really sensitive to the distribution, right? If you're working in the the multiplicative group mod P, DDH is false if you actually choose your exponents uniformly in Z sub P minus 1. You have to make sure that you are in a subgroup like here. So what we want is a way to go from our algebraic crypto assumptions to whatever our minimal assumption is in a way that's relatively robust to changes and not super sensitive to the details. Okay, so here's the simple to define. One-way functions are really easy to define. I can define them in one line. Whereas like digital signatures, you'd have to have this whole interactive game and all that. So this one, hopefully self-explanatory. Another one is we want it to be falsifiable. And there's subtly different notions of falsifiability in the literature, but I'm going to take the sort of imprecise version, which is just it's defined by an interactive game between an adversary and challenger. So are signatures, so are most of the things we care about, but things like NISICs or whatnot would not fall into this category. Not trivially. Related to some of the things before, we would like a search problem. Generally, search problems are milder assumptions than the corresponding indistinguishability assumption. They're more robust, as we saw with the discrete log versus DDH example. So search problems are probably more likely to be minimal than a decision problem. Here's another one. Maybe this one is optional. I don't know.
Why is it obvious that search is better?
I mean, it's not obvious, I guess, in just on the face of it, but at least as it relates to some of these other things we would want. Search assumptions are more robust. They tend to be milder, right? Like discrete log is a milder assumption than DDH. And also they often tend to be simpler, I guess. So here's another one. So combiners. So with one-way functions, if you have two candidate one-way functions and you don't know whether they're secure, but you have the guarantee that at least one of them is secure, it's trivial to get a one-way function that's guaranteed to be secure, as long as at least one of the input one-way functions is secure, what do? You just your input is now an input is two inputs, right? It's a pair. One input for the one-way function, that should be F2 over there. Another input for the other one-way function. And if you can invert this new combined one-way function, then clearly you're actually inverting both one-way functions. So as long as one of the two is hard, then this combined one-way function is hard. And this feature of having a combiner allows you to actually get something that's called a universal one-way function, which is a single fixed one-way function that is secure as long as there exists a one-way function that is secure. You don't know what it is, but as long as there is some one-way function that's secure, this Goldreich one-way function will be a secure one-way function.
Sorry to keep doing this, but I think that's actually a result of Leon and Levin.
I see. Okay.
Much earlier.
I see. I blindly am copying citations from other works, and apparently, I don't know about the previous one, but this one I definitely copied from a paper.
Maybe
So
you're citing the book.
Yeah.
Which cites,
yeah, probably.
which cites the
The
paper.
book has a tautology. There exists universal one.
I need that.
Let's put it this way, you're doing better than ChatGPT.
Yeah, I actually was curious. I asked ChatGPT to define indistinguishability obfuscation, and it came up with something that kind of sort of looked okay if you skimmed it, but it was actually totally wrong once you actually read the information. So ChatGPT definitely doesn't understand crypto. Not yet. Okay. So this is a nice feature, and what it does is it actually makes one-way functions a nice hub, and allows us to use the one-way function combiner to actually get a combiner for a lot of symmetric key crypto. You want a combiner for pseudorandom generators? Well, you got one, right? You go through one-way functions. You want a combiner for pseudorandom permutations, signatures, whatever? You got one. You go through one-way functions. And the interesting thing is in that a lot of these cases, this is the only way we know how to get a universal construction. We don't know how to get a universal construction of, say, pseudorandom permutations directly. There's as far as I know anyway, there's no direct construction of a pseudorandom permutation that's universal. But we can do it because we can go through one-way functions. And then, so this is going to be related to the previous one and also about simplicity. We really want, we want there to be a definition that really there's a security property and kind of nothing else, right? And if you think about things like signatures, pseudorandom permutations, whatnot, they're correctness properties, right? Signature, we need that there's this verification algorithm that verifies signatures. Pseudorandom permutations, we need that the functions of permutation and also that there's an efficient inversion algorithm. Whereas one-way functions, there's really nothing. We require deterministic procedure. That's basically it. Classical deterministic procedure. PRGs are basically require nothing, except we do need the function to be expanding. So there's like a little tiny requirement. But yeah, pseudorandom permutations, there's pretty strong correctness requirement. And this is actually related to the previous point about universality, in that if you have two pseudorandom permutations, let's say, and you're guaranteed that they're both functionally pseudorandom permutation, or sorry, you're guaranteed that they're both permutations functionally, that there's an F and an F inverse and they actually invert each other, then it is actually trivial to combine them. You can just compose them and you're done. But the problem is for a universal construction, you actually need not just that you can combine the security, but you sort of need that you can identify when an algorithm actually satisfies the correctness requirements. And so really what helps for getting a universal construction is that all your correctness requirements are semantic. Yes.
Would you say that security amplification is also an important feature?
Yes, I didn't put that in here, but yes, that is a good feature as well to have. Right. So Right, and so one-way functions, the only correctness property is semantic, it's just deterministic classical function. And what this allows you to do is you can actually enumerate all possible classical deterministic functions, and this is really crucial to getting this universal construction. In contrast, there's no way to enumerate all possible pseudorandom permutations. I will point out that this is not a necessary condition for there to be a universal construction. For example, we can get a universal construction of PRPs by going through one-way functions. Or we have universal constructions of indistinguishability obfuscation that are direct from indistinguishability obfuscation. They're very complex though, and there's like several papers to actually get them. But I guess the point is though that having a minimal correctness requirement really helps make the universal construction much nicer. Okay, and then the last feature is kind of maybe one I should have started with, which is that it's actually useful that you can build crypto from it. We don't want something that's way beneath crypto mountain here that's totally useless for crypto. So this is obviously a crucial feature. If I can define a minimal assumption that is implied by everything but doesn't do anything at all, then there's kind of no point. Okay, so I don't want to step on. Oh yes.
There's another non-mathematical feature of one-way function, and it's a social reason. It's defining difficult and it's getting a lot of traction, so that's why people think one-way function is minimal instead of single.
Fair enough. And yeah, that could totally happen too in the quantum space if prominent enough paper sort of claims to have the minimal assumption. I think right now the main contender are the EFI pairs. But I think also one-way functions do have a lot of nice properties that even if it wasn't defined by famous people, maybe we would have converged on it anyway. I don't know though. So I don't want to step on any of the other talks today, so I'm going to just talk about two examples of less than one-way function quantum objects and see how they fare. So the first one is pseudorandom states. So this was defined by Ji, Liu, and Song. And I think at the time, they didn't actually claim anything about being beneath one-way functions. It was kind of realized after the fact. I could be wrong, but the point of their work was to define this object, not necessarily to explore the below one-way function space. But nevertheless, this emerges kind of an early example. So what is a pseudorandom quantum state? So it's kind of like a pseudorandom generator, except that the output is a quantum state. So we have this quantum procedure G that takes as input a classical seed and outputs a quantum state. And I'm just going to call the input length lambda and the output length n qubits. And I'm not going to define security precisely, but we want that the output state looks random even under polynomially many copies of the state. Right, in quantum land, we have this no cloning theorem, which means that if you want to have multiple copies of something, you actually need to be provided them. You can't get them for yourself. And as you manipulate them, you might accidentally destroy them. So having multiple copies potentially gives the adversary more power to try to distinguish. Right. And now it turns out that for this, you need crypto. For a classical pseudorandom generator, you need crypto as long as n is greater than lambda. For pseudorandom states, it's a little different, basically because the space here is there's an extra exponential in the hidden space of a quantum state. So really, you need crypto as long as n is greater than log lambda. That's if and only if there's a tight threshold. Right. Okay. So how does it fare against my criteria? So trivially implied by general primitives, this is not true. So the constructions we have go through pseudorandom functions, and I think they all go through pseudorandom functions. Certainly the original ones that did. And this required, not only something like Goldreich-Levin and GGM and all that to get classical pseudorandom functions, but actually needed to be secure against quantum queries. Which means you need a quantum version of Goldreich-Levin, you need a quantum proof of GGM, which all those require their own papers. Similarly, it's not trivially and robustly implied by any concrete assumption, as far as I know. It is pretty simple. It's not, as simple as a one-way function. You have, this polynomially many copies business, but it's pretty simple. It is certainly falsifiable. Pretty much all the proposals out there are falsifiable. This one's easy to satisfy. Yeah.
Really annoying question, but I think it's written in JLS. It's not clear how you falsify, right? The challenger needs to sample arbitrarily many copies of a random state, like for unknown polyvalent.
Yes.
That's true. I imagine you can. I imagine you can, sample things efficiently. And, yeah. Okay. Fair enough. Fair enough. So even falsifiable is a question mark here. I was giving them too much credit. Yes.
Is the state? Are you have a way of producing the state? Or
Yes. This is the G here.
So then, if you're given the G, you should be able to make any number of copies, right?
Right. So in the security experiment, though, you're either given polynomially many copies of this, or you're given polynomially many copies of a random state, and that's the part that is not necessarily trivial to sample.
Don't do that.
Just because you can't write down a random state in any finite precision. It's kind of a simple reason why you can't do this. Yeah, so the one side of the experiment where you're producing these is easy. It's the other side that's hard. The side that kind of plays the role of the random string in the PRG definition. A search problem it fails. It's a decision problem. Combiners and universal constructions, we have no idea. And in fact, it's actually non-trivial or even not even known to go between pseudorandom states of different output lengths. Correctness requirements, we're kind of in the same domain as PRGs here. There's one correctness requirement, which is unique to expanding. Procedure and useful, their applications to quantum money and other things. Yes.
Is it possible that the first two are actually many of these things are just because we don't know quantum well enough yet? We don't know how to do things trivially. Maybe there are trivial
Possibly. Yeah, it's certainly possible.
Figure it out yet.
Yeah. Absolutely. I will say though.
Combiners.
What was that?
How can you rule out combiners?
I can't. Yeah, certainly this is based on the current state of knowledge. But if
the classical crypto has much more, many more years of experience.
Absolutely. But thinking of 1 and 2, for example, like any undergraduate in a crypto class, if you ask them to construct a one-way function from, Diffie-Hellman or something, they'd probably be able to figure it out. Whereas I wouldn't have known. Whereas it was highly non-trivial and required a whole body of prior work in order to get pseudorandom states from.
I don't mean to argue. I like this direction, but I think you should give the same talk in 20 years again.
Yeah, absolutely. So yeah, these are absolutely based on the current state of knowledge.
So then why did people like this definition? If it's so hard to get, and why is this?
Because it's useful. It's useful.
Function is also useful. Why do we in which sense we think this is more minimal than one function?
So well, basically we know that there's a black box separation that you can't get. You can't in a black box way build one-way functions from pseudorandom states, and yet one-way functions apply pseudorandom states. So just from a feasibility perspective, these live below one-way functions, and the question is, okay, they live below one-way functions. Maybe now we can have a whole bunch of cool feasibility results that don't rely on one-way functions but rely on something even less, or potentially even less than p, maybe p equals np, and you can still do crypto. So that's why people are looking at these, and yeah, and we have black box separations that show that these things don't imply one way.
Yeah, but this is, yeah, but like you said, you gave the example with signatures. This is all very, like, what's below what, right? Like, for example, you can construct this from, let's say, CRH, but you cannot construct CRH, like, but we know it.
Yeah, certainly some things can be incomparable.
Right.
Yes.
Yeah, but this is more complicated, right? It's like somehow you can require less assumptions and still be more complicated. So it seems like there's maybe multiple dimensions here that you.
Yeah. I mean, the hope, my dream is that there is a primitive out there that just is obviously implied by, all pseudorandom states, EFI pairs, anything you name it, trivially implied by it, is useful for crypto, and maybe satisfies like a number of these other requirements, simple, has combiners, whatnot.
Would you have liked pseudorandom states more if you could construct them sort of directly for one-way functions without going through PRs?
Yes. But as it stands, like, if things were out of order and quantum had been hot in the 70s or something, like, people would be proposing this and thinking that this is stronger than one-way functions potentially.
Right. Yeah. This does not look minimal, I think. Yeah.
I agree. Even though, from a feasibility perspective, it's less than one-way functions. I agree. I don't think it's minimal. And this is, my attempt at at least partially explaining why. Yeah.
Something you said, but did you say that the existence of these things does not even imply that these not
What's the question?
Certainly some of these primitives. I don't know about all of them.
Mark, what was the question?
The question is whether you can have P equals NP and like pseudorandom states exist. I think you can.
Like, stay tuned, right?
Yeah.
Yeah.
Yeah. It's.
Single copy is no application, and many copies has some.
I see. Yeah, like I'm certainly not the foremost expert in this area, and it's moving very quickly and is very complex right now. So I'm not going to go. I can't claim that like everything beneath one-way functions can exist if P equals NP, and it's rather nuanced. But certainly some things can exist. Yeah. Okay. So this is the last. I'm only going to talk about two things. Here's the other one. So one-way state generator. So this was proposed by Morime and Yamakawa, and the motivation is, okay, the pseudorandom states are kind of like pseudorandom generators. One-way functions are, more minimal than pseudorandom generators in some dimensions at least. So let's try to get a one-way function-like object that's related to pseudorandom states. So this is what they came up with. The issue with one-way state generators is just that it becomes non-trivial to actually define what it means to invert the one-way state generators in a meaningful way, because you could have it just that it's information theoretically uninvertible. For example, this is what quantum money gives you. So they had to define this extra verification procedure that takes as input a state and a candidate for what the original classical input was, and it accepts or rejects. So,
How can it be information theoretically uninvertible?
I mean, think of quantum money.
It's a pure state, right? It's like,
yeah, pure state that depends on S though. So
Right,
think of
yeah,
quantum money, for example.
can they go over all possible S's and check?
No, because you have
don't
to apply
sufficiently many
measurements.
copies?
You have polynomially many, but
No, I
you
have
don't-
many copies, so I could do topography on them or something like this.
Cryptography requires, because the dimension's huge here, right? I don't think it's trivial. Yeah, I mean, I guess the known constructions of quantum money can work if you have polynomially many copies, but in general, it's not obviously.
Sorry, why is this implied by general quantum money?
I take it back. It's not. It's just the fact that you could have information theoretic.
Okay, let's say public key quantum money.
No. Information theoretic secret key quantum money.
Right, but is this implied by public key quantum money, which cannot be information theoretic?
Yeah, I don't know. That's a fantastic question. So, most of the study of this like less than one-way function crypto has focused on things like building commitments and stuff like that. And it, to me, intuitively, at least, it seems like it's relying on a different source of hardness than things like public key quantity.
So maybe not even number one should be a secret.
Yeah, it might not be. But it's implied, it's at least implied by all classical crypto. Right? So it's implied by a lot of things. Yeah, maybe not quantum money, maybe not some other things. But it's implied by a lot of things. I also don't think it's implied by commitments. But okay, maybe this should be a question mark or something. So also concrete assumptions give these. This I would say is not simple though. It it has this extra correctness requirement. It is a search problem, but because of this correctness requirement and maybe other reasons also, there's no combiners, at least none that we know of, for options. Yeah.
I have a similar comment to what I said before, but about simple, it may also be what we don't understand. So for example, I would say the definition of P is not equal to NP is not simple if you just give the formal definition without any explanation. But it is really simple because we understand that it says something very
Sure. It depends on
simple and
context.
clear. So somehow, I don't know, this is just a comment. Like, how would you consider the definition of P is not as sad as hard in the worst case? I don't know. P is not equal to NP. How would you consider it simple or not?
Relatively, maybe not as simple as one-way functions. I don't know.
Deterministic, whatever, or verifier or something.
Yeah, fair enough.
Common knowledge.
Yeah, so I think it's simple based on understanding because we understand what it means. It is simple. So maybe, we will understand.
Right.
that this
But
is really
I guess what will it take for this to be, really simple? Like you're already starting off the bat with like a security requirement and a correctness requirement. It's already more complicated than say one-way functions, right? And yeah, maybe some context would help with that, but I don't know. I guess I'm skeptical, but yeah, you're absolutely right that maybe these things get easier if we develop a sort of better understanding of what's going on. And that's really it. I just wanted to leave us with the possibility that maybe there actually isn't a good minimal crypto assumption. That maybe actually the beneath one-way function domain is going to be a mess, and it's inherently a mess, and we're never going to fix that.
Maybe it's not true, there are no assumptions.
Or maybe there's no assumption, in which case we should all go home. All right, and that's it. Thank you.
Okay, so while Fermi is setting up, is there any more quick questions or comments?
Also, quantum complexity not dictate, like, is there anything meaningful to say in terms of complexity?
You mean like P equals NP, classical crypto is dead, that kind of stuff, or what?
Yeah, sure.
I imagine there's some analog of P. I imagine there's some analog like P that apply that quantum this. That should be. What?